Okay, we can say that a function is continuous on an interval if and only if it is continuous at every point on the interval. For example, that semicircle function we looked at was continuous on the interval -2 to 2 with closed brackets. That is its domain, because that's all the places that it's continuous at. A continuous function is one that is continuous at every point of its domain. A continuous function does not need to be continuous on every interval. So as long as I set up a domain for it, then whenever I'm looking at the domain that I can set up, then I can decide where it has to be continuous at. So by restricting a domain, I can make it continuous on that domain, and it doesn't have to be continuous everywhere in the function, only where I'm looking at. Today is going to be a lot of writing, a lot of rules that we're going to discuss today and moving forward. The function y equals 1 over x is a continuous function because it is continuous at every point of its domain. It has a point of discontinuity at x equals 0, however, because it's not defined there. So think about the function 1 over x. I can't divide by 0, so 0 is not in its domain. But this would be considered a continuous function because it's continuous at every point in its domain. 0 is not in the domain, so it is discontinuous at x equals 0, but only because there's no x equals 0 in the function. Since I can't plug x equals 0 into the domain, it tells me that this would be a continuous function, even though it clearly is not continuous looking, because this point here is not in the domain. Theorem 9, properties of continuous functions. If the functions f and g are continuous at x equals c, then the following combinations are continuous at x equals c. I can add the functions, I can subtract them, I can take their products or multiply them, I can multiply them by a constant or just by any number. I can divide them as long as the function on the bottom, in this case g of c, is not equal to 0. And I can take them to a power, provided that it's defined on an open interval containing c, where r and s are integers. In other words, I can't have r and s as fractions, and it has to be the interval that contains c. So again, I realize it's a lot of writing today. But that's why our notes are going to be, at least class is a little shorter, because I'm allowing you the time to write it. So just pause the video as you need to, so that you can get everything written down. Polynomial and rational functions are continuous. So every polynomial, that's p of x equals any number times x sub any power, plus the next one, plus the next one, all the way down to anything. So as long as it's a polynomial, then I can say that it is continuous. Let's see my issue here. This should be a superscript, not a subscript. That's better. And now I have a superscript end. This should be a superscript, which means it's an exponent. Anyways, as long as I have x to the nth power, so that could be x to the 5th plus x to the 4th plus dot 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 going down forever until I don't have any more x's. It's continuous because the limit as x approaches c of a polynomial function is equal to just plugging c into the function. And that came from theorem 2, which was in section 2.2. So because my limit exists, I know that that's going to work. Part B of this is that if p of x and q of x are polynomials, then the rational function is continuous wherever it's defined by the quotient rule, as long as q of c is not equal to 0. So as long as my denominator is not equal to 0, then it's going to be a rational function everywhere. Whenever my q of c is equal to 0, we would simply restrict our interval to not include where it's equal to 0. Theorem 10, composite of continuous functions. If f is continuous at c and g is continuous at f of c, then the composite is continuous at c. So the first thing this says is that I have a function f that's continuous at c, and then if I plug c into f and I take g of f of c, remember Fogg and Goff from last year, if I have g of f of c then this composite would be continuous as long as g is continuous at this point. So I would be plugging my c into f. If it's continuous there, then you would plug that in for g. With composite functions, there can be a little graphic that's a little helpful for us just to look at. And so if I look at this graphic here, if I have f continuous at c and g is continuous at that point, then their composite g of f is continuous at c. It's like taking two little leaps here, and that's equal to the same jump from the beginning to the end. All right, let's apply theorems 9 and 10. So first is theorem 9, which said that we can subtract these things and they're going to be continuous. And then theorem 10 says that I can take the composite of it. So if I look at this function, the square root function itself is continuous from 0 to infinity. So the square root of just any number is continuous from 0 to infinity. Why? Because I can take the square root of any number starting with 0 and going to infinity. I can't take the square root of a negative without coming up with a complex or imaginary number. Additionally, I know that this is true, that the square root of any number is good from 0 to infinity, because it's a rational power. Square root of x is the same as x to the 1/2, which means that this is a rational power, which comes back to my r over s. Function raised to the r over s. R is an integer, s is an integer because it's 1 and 2. And so that's another reason that my square root function works. Then our given function, which is the square root of all of this, is the composite of the polynomial f of x equals x squared minus 2x minus 5, and g of x being the square root of x. So I just showed why the square root works, And then f of x is just a polynomial. And all polynomials are continuous. So this function would be continuous on the interval from 0 to infinity. Let's look at this one. So I have a rational function here. And so this comes back to number 9 here. Theorem 9. Polynomial and rational functions are continuous everywhere that q of c, or my denominator, is not equal to 0. If I look at this actual function, my top function is continuous. So this would be my f of x. It's continuous because it's got a rational exponent. So the top is continuous. I would need the bottom to be continuous, which it is. It's just a polynomial, 1 plus x to the 4th. Now this polynomial in the denominator, the only time where this would not be continuous would be when this denominator is equal to 0. However, in this case, this denominator will never be equal to 0 because I have an x to the 4th. No matter what I plug in for x, it would give me a positive number added to 1. So this is always going to be positive in the denominator. So there's no way to make my denominator equal to 0. So the quotient is continuous. Looking at this one, we have x sine of x over x squared plus 2. Now the sine function is going to be everywhere continuous. So it's continuous on every interval. The numerator, which would be x times the sine of x, is the product of two continuous functions. X is continuous, and sine is continuous. So since this is always continuous, and this is always continuous, theorem 9 says their product is always continuous. So my top is always continuous. On the bottom here, I have x squared plus 2. That denominator is an everywhere positive polynomial. In other words, I can't make that equal 0. And I can try to make it equal 0. If I set it equal to 0, then I would just solve this. X squared equals negative 2. You can't square a number and get a negative. So this could not happen. I can never make it equal to 0. So this will be continuous everywhere in the numerator and everywhere in the denominator. Since we're dividing those and it's continuous everywhere, the whole thing would be continuous, but it's still inside the absolute values. So looking at the inside of the absolute values, the absolute value is also a continuous function. There's no number that I can plug into an absolute value to make it not continuous. So basically, this was continuous, this was continuous, the bottom was continuous. So multiplying these two gives me a continuous function on top and a continuous function on bottom. If I divide those, it's still going to be continuous. And I'm taking the absolute value, so this is a composite function, and the absolute value is continuous, so the whole thing stays continuous. Continuous extension to a point. And I just want you to write this down and then we'll stop and get into this tomorrow. So So if I'm doing a continuous extension to a point, I have a function y equals sine of x over x. That would be continuous everywhere except where? The only place that this wouldn't be continuous, remember what we just learned, sine x is always continuous. It's a continuous everywhere function. The only place that this wouldn't be continuous is at x equals 0. So since that wouldn't be continuous at x equals 0, because I can't divide by a 0. So then I can add make an extension to the function by setting up a piecewise function. So what that's saying is, if I look at my graph of what sine of x over x looks like, looking at this graph, I can see that if I do a trace on it, as my x gets closer and closer to 0, my y gets closer and closer to 1. So my limit of the sine of x over x as x approaches 0 from the left is 1. My limit as it approaches from the right is also 1. See, my y just keeps getting closer and closer to 1. But when I hit directly on 0, it's undefined. So I have this one spot here where it's undefined. We can actually fill that dot in by creating a piecewise function. So we can create a function that's what we have already, sine of x over x everywhere and x is not equal to 0. And then I can say when x does equal 0, I want to fill that dot in. So that tells me that it's always going to be 1. Now this function would give me everything continuous everywhere except 0. And now this says when x equals 0, it's 1. So I essentially had this function that went up, and I had a hole at x equals 0, and went down, and that was just sine of x over x. And now I took, by adding this part in, saying when x equals 0, y equals 1, I filled that dot in at y equals 1. So now it's continuous absolutely everywhere. This extension allows us to create a completely continuous function just filling in that hole. All right, we'll get into this more tomorrow, set up more extensions to functions, as well as do some more examples from figuring out if it's continuous everywhere and why. And then we'll move forward with just more examples.